questions about things you know, and forgive me if they're already obvious. So if I draw a basic 4 to 20 loop, and I realise you're all over this like a rash, but here's a gas burner, here's a vessel we're heating, we're controlling that gas burner with a electronic valve, and that's going through a power supply, which will be a battery in this case, through either a PLC or a whatever controller you're planning to use, and you're forming, and then you've got a thermocouple or whatever temperature sensing device you have in the vessel, feeding into there and feeding back to here. And of course we have a loop here which varies in current 4 to 20 milliamps. I realise I'm preaching to the choir. 4 milliamps representing 0, 20 milliamps representing 100%. In this sort of setup, many things can go wrong. Most typically, the sensor that's in contact with the fluid gets corroded or worn out. So maybe, let's say it's a thermocouple. Maybe the thermocouple's failed. Maybe the controller is not responding in a linear fashion to the thermocouple that's in there. It's not converting the millivolts to the temperature. Maybe the output of the 4 to 20 is not correctly scaling for 4 and 20. Maybe the power supply is noisy or non-functional. Maybe this valve is not responding to 4 to 20 in a fashion that you would like it to. So the idea of the 221 is it can fault find and simulate absolutely everything in that circuit. Now, of course, as you probably know, in the real world, you might have another transmitter in the head, especially if it's going over a long distance. So let's say there's another transmitter in here. So there's actually a second 4 to 20 milliamp loop on that input side. All makes sense so far? So, and I've drawn this much more nicely. You've got booklets there so you can look at it later on. So, let's say phase 1, what do we do? Someone's called you up and said, hey Colin, the acid tank is not heating correctly. So it could be any number of things that might have gone skew-whiff. So let's assume for a start that it's the thermocouple. We can simulate that. So on the instrument, we have 2 screens, source and measure. And then each selection of the settings toggles you between source and measure. So for example, if I hit thermocouple RTD, source measure, source measure, source measure. Yeah. So it's quite intuitive. So in this case, we might say, well look, why don't we simulate a calibrated thermocouple, so we'll say there's no transmitter in this case. Let's simulate a thermocouple at 300 degrees Celsius. So let's produce a calibrated type K thermocouple signal as if it's 300 degrees. And it's completely calibrated. You put your hand on a stack of Bibles and know the output is right. So on the top of the instrument, you have 2 thermocouple sockets. One says measure, one says source. So what we're wanting to do is pretend that we're a thermocouple at 300 degrees C, and we want to see that this is 300 degrees C. We want to see that perhaps this gas controller responds at different temperatures. So we might ramp it up and down. I'll show you that. So what we want to do is source a K-type thermocouple. You see why?
Yeah.
Makes sense? Yeah. So if I hit the thermocouple RTD button, source measure, so we go to source. Now it will default to type K because, as you know, in New Zealand that's by far the most common. But if you guys go and do some work at AW Fraser or something that's using metal, if you go use the cross arrow, you can select other thermocouples. So ST, all the exotic ones. In the plastic industry, T is common. In the molten metal industry, S or R is popular. So you can select any of those. But in 90% of the cases, you're going to be type K. And you also, you know that every thermometer has a cold junction reference within it. And that's what we're using here. So we're saying we're going to use the internal cold junction reference. And again, 99.99% of the time you will. But there might be a time if you were working in a particularly hot environment or something, you might want to use a separate never come across it, but you might. So let's say we want to simulate 300, let's make it harder, 301.5 degrees C. So I've just typed that in, enter. Now, coming out of the source terminal is a calibrated 301.5 degree signal as if it was a K-type thermocouple at that temperature. So you can see we've got an internal reference cold junction calibration of 17.25 degrees, and it's at 11.562 millivolts. That is a hand on a stack of Bibles signal. So you'd have a lead like the ones, oh, I left them behind accidentally. Oh me, oh my. So you take a lead like so, plug it in the right way around, connect that in place of where the thermocouple was, or perhaps into the controller. And of course, straight away, what you should see on the screen, if it's a standalone controller or a PLC with an LCD, you should see 300 degrees on there. You should also see the flame behave as if you'd expect at 300. So if your set point was 400, you'd expect the flame to be going hard. If your set point was 250, you'd expect the flame to be nothing. By the way, I'll just do a quick aside. I'm sure you've come across this, the bizarre American color coding on thermocouples. Red is negative. You've come across that before, have you?
No.
Okay, if you're ever using thermocouple cable and it's an American color code, on the back of a Home Machines catalogue, which
don't have one.
Because well, you've got the worst rep in the world. I'll get you one before I go. The American color coding, I mean they elected Trump. They have red is negative.
Righto.
Bizarre. But anyway, that's just by the by. So let's say we now want to say, well that seems okay. It implies the power supply is okay because we've got the flame. Let's make it ramp through a range of temperatures to see what this flame does and see if it goes up and down.
The valve response.
Yeah. So you see here at the bottom of the screen, there's a LCD ramp.
Yep.
So so F3 button. These are soft buttons. So if we hit F3 for ramp, we might say we want to ramp between 100 and 400 degrees C over 60 seconds, for example, and I want to do it in 0.2 degree steps, and I want it to repeat up and down, up and down, up and down. Connect it up as per this, and we go, I'm no good upside down, it's all my first wife left me. Start, you can see the temperature climbing in 0.2 degree steps.
Yep.
And what you'd see here would be the flame going up and down. Just bear in mind, if you're doing this, you're on a live system, so you have to use some caution because you don't want to be cooking whenever you're doing. But you can see that's marvelous, and as you raised with the valve, you'd watch your valve opening and closing. And you could do the same with the other functions. So let's say you've determined that you think that this valve is not responding as you think it should. You could, instead of doing a thermocouple signal, testing the entire loop, you could have just a 4 to 20 milliamp signal injected in here. So if I exit that, remember source measure. So if I select milliamps, source measure. So I'm going to source milliamps, and we could put in 20 and inject that signal, and we would expect the valve to go fully closed. Now, when you're sourcing current, it's slightly different to when you're sourcing thermocouples for a couple of reasons. One, obviously we're not using thermocouple sockets. This side that's the lighter grey is your source side. This side, which is the darker side, is the measure. How you're sourcing current is going to depend on whether you're going to use the internal loop power supply that's there, or whether you're going to, if it's on your bench, and you want to use the 24 volt that's on board, because it has 24 volts on board. In this case, we're doing it in situ, so we're going to assume there is loop power there already. So we're going to come off milliamps there and there. So you'd simply go, perhaps a banana plug into the input. And the same thing could happen. So we could go 4 milliamps, enter, and the valve should open. 20 milliamps, enter, valve should close. Or I had this in a real case. I was at a plastics manufacturing facility and he had a Modutrol controlling gas burners and it was hunting. So I went to 12 milliamps halfway and it was hunting up and down. And I said straight away, that's your feedback potentiometer on your Modutrol. And the Sparky was like, I've been here for 2 hours trying to fix this. He was right, Peter. And again, you can do the whole ramp thing again. So again, just be aware of the process is actually going to do what you tell it to do.
Yeah.
But you could say, ramp. Let me see your ramp between 4 and 20 milliamps over 60 seconds, and again, repeat up and down. Connect it up and start. And again, watch the valve open, watch the valve close, watch the flame rise, watch the flame fall. So it's horrendously wonderful, you know, for doing this sort of thing, for testing it out.
How do we use the onboard 24?
Okay, that's an extremely good question. So you've got the thing on the bench. This won't have enough current to drive a valve, obviously. It's only going to drive the 4 to 20 milliamp control signal. In the case of using it on the bench, the 24 volt supply is isolated. Those in the know tell me that's a really good thing. So what we need to do is take the ground and common that to where we're going to take the current. Now we're taking 24 volts and we're going to go there and there again. Actually, that's wrong. We're going to go there. No, I am right. We're going to go there and there, and we're going to go there and there, and now it's going to be the 24 volts as well. So you're now going to be generating the 24 volts as well as not just acting as a variable resistor.
Right. Just from looping those two.
Yeah, I think there's an example in here. If not, I'll send you a photo. I did some photos of common setups. No, it's not in here. I'll send that to you. There's also, by the way, if you get really stuck, go back a step. All the inputs are protected for up to 30 volts. So if you're working on a loop circuit, don't panic too much about getting it wrong and cooking it, because they're protected up to 30 volts. So on a loop system, quite often I'll go, was it there or there? And you could even, if you were testing it the first few times, you could put a multimeter and see, am I getting a variable voltage, or am I getting 24 volts that represents that current? Okay, I'll send you the common photos of common setups.
Yep. Fused.
Eh?
Fused.
No, it's electronically protected. That's why it's 30 volts. So you can just pretty much go, what's that? No, because it provided you at 30 volts. I think it's 30 volts 1 minute. So if you get something wrong, it's not the end of the world. You can even, I've not seen this done very often at all, you can even simulate the transmitter. Let's say you thought that the transmitter in the head or the transmitter on the rack was dodgy. You can actually put the thermocouple or the RTD into here and have it act as the transmitter and give you the 420. So have this replacing the head mounted. So it really does absolutely everything in the loop. Now, a couple of extras. Obviously we have 3 and 4 wire RTDs. You know about those?
A little bit, yeah.
Do you know why they have 3 and 4 wire RTDs?
No.
Because some people think it's just because you're going to put more copper in the way and it makes it less resistance. It's not, it's cleverer than that. As you get more and more wire, you get more resistance, of course. So what you can do is, you know what a Wheatstone bridge is?
Yeah.
So you've got your 4 resistors. I'm the worst artist in the world. Yeah, there we go. If we put a voltmeter across there and we put the voltage in here and here, we get 0 when all these are equal. With a 3-wire RTD, you'll notice that the RTD is a resistor. You've got 2 leads off one end and 1 lead off the other.
Yeah.
People think, well, that makes no sense because they're in parallel. It's just, why don't we just use 1 wire? Well, at the measurement end, they put one of those leads in series with the Wheatstone bridge, one going straight through, and it means that it compensates. I've drawn that very badly, but it compensates for the lead resistance. So it actually nulls out the lead resistance on one wire. And then the 4 wire just makes it more complex, but it's much harder to draw. So yeah, 3 and 4 wire RTDs are useful if you've got long runs and you want to get the resistance. So you'll see on here, when you're measuring, you've got 2, 3, 4 wire RTDs you can measure on there.
Oh, right, yes.
When you're
Okay.
simulating, there's only 2 because you're at the instrument, so the lead wires are of no benefit. So for simulating, RTDs right there, just 2 for good reason. And again, it's exactly the same. So source measure. So if we go to volts, now on this one you've got some choices. You've got millivolts, volts, frequency, pulse counts, and you can source and simulate. So imagine, for example, with pulse counts, if you've got one of those flow meters that has a pulse output, 1 pulse per litre or 20 pulses per minute or whatever it is, you could simulate, if you know what the flow meter should be. So you go to the manufacturer and say, hey Homishams, that flow meter you supplied me with the pulse output, what is the rate of pulse? So you can simulate precisely that. So I could go to pulse and say, 20 pulses, what should the flow meter be doing? And then it generates that. Way cool. I love selling these things. But anyway, back to voltage. So if you've got an RTD, you might look up a table. We might just go to volts. And if you happen to know that a PT100 is 100 ohms at 20 degrees C, which it is, you could then put in 100 ohms and see what it does at 20 degrees C. And again, make it ramp, make it do things as well. So we could go, sorry, I'm saying volts, not ohms. Duh, wake up, Greg. So we're going to ohms for a PT100, 0 to 400 ohms.
Why don't you just go to RTD?
That would be the other way to do it.
Yeah.
Same thing. And the advantage of going to RTD is that it's got the various different curves, because not every RTD is the same. In this case, we have an RTD 385, which means it's 0.385 ohms per degree C. There are other curves of RTDs.
Okay.
Again, 99% of the time, yes, you'll be using a PT100 with a 385. But very occasionally, you might come across a PT100 with some weird curve, and this covers it as well. So it really is the coolest instrument ever. I never regret selling these. You go to people and they come back to them years later and go, I didn't know it did that.
Oh, yeah.
Yeah, if you get really stuck, as I say, I'll send you a couple of photos of common setups, but there is within the help menu some diagrams you can use to set it up as well. So if we go to help, about product connection diagrams, electrical measurements, that'll do. It shows you some of the setups.
Okay.
Nice.
So that's quite good if you get stuck, because the manual is hopeless. The manual is only software, but it's only electronic, but it really is crap. But that's useful. Okay, what else shall I show you? It's got what I like to facetiously call apprentice mode.
That's right, yeah.
That is, you can set up tasks for someone who doesn't know as much. I call it apprentice mode, but it could be for anyone. So for example, if you had in the factory, let's say you've got a whole lot of big digital displays up on the wall, 4 to 20 in, and they display a temperature from the process, and you want your tech to go and calibrate all of them. You can preset that as a task. And just say, go and perform task 1 on every one of those setups. So we go to task menu. Oh, we get out of that one first. Back. Okay. So we go to the task menu, task list, enter on that. There's task in there that I will have created, so I'll just delete that one. Delete this task, okay. So let's say that's precisely the situation. You have all these digital displays and you want someone just to go and check, say just the as found. So you would go into a new task and it brings you up a list of things. RTDs, thermocouples, flow meter, so let's say in this case that it's a loop display. RTD indicator, no, we're not on a loop, we're on, there we go. Thermocouple indicator. No, I'm on thermocouple again. Loop, there we go. We've got loop indicator. We'll use that one for example. So you call it whatever you want to call it. Colin's task today, temperature, humidity, all the standard settings. You tell it what sort of input it's got. Now it's defaulted in this case to volts, but we actually want to have milliamps with or without 24 volts. So we'll say milliamps without 24 volts. So you're going to use it in situ. And we want to go from 4 to 20. Linear, yes. Next. And how many calibration points do you want? You can have as few as 2 and as many as 12. So this is for if you're doing an actual calibration. No one's going to do 12, no one's going to do 2. Most people are going to do 3 or 4. So what's it got in there at the moment? It's got 5 calibration points. Let's do 3. So it's going to test it at 4 milliamps, 12 milliamps, 20 milliamps. And we've said that 1% is the acceptable tolerance. Now I've chosen a bad example. I should have chosen a more automatic one that had a transmitter, for example, because this will require manual entry. The person's going to have to look at the screen and go, I'm at 4 milliamps and the display's reading 4.3, and you type that in. I'm at 12 milliamps and it's reading 12.7, and enter that in. If you had an automatic mode, it would measure. So if you were calibrating a transmitter, it would give you the actual output. It would produce a graph. So let's say we will do that. We'll do the calibration. We'll go select that, and we'll go, let's do an as found test. So in this case, the instrument's producing a 4 milliamp signal, and you're going to type in what you see. Okay, we're getting 4. That'll do 3.994. We'll accept that. Then it goes to 12 milliamp, the halfway point, and we're seeing on the display, you know what I'm saying? We're seeing 13.5 milliamps, and we accept that. And then at 20 milliamps, we're seeing 20 milliamps. Now it's drawn you a graph of what the result of that display is. Now, if it's so we'll accept that, and then it will do the same on falling, because you want to allow for hysteresis. So we'll do the same again. We'll say it was fine, it was fine, it was fine, it was fine. And it will draw a graph. Oh, accept. So in this case, there's your summary. On rising, it was really crap. On falling, it was really good. The acceptance ratio here is the acceptance criteria we said was 1%. This one fails. You could now save that as an as found report, and then the tech could come back to you and go, here's the results. Then you could send them out, do a calibration, do an as led. If you have, it doesn't come with it, but you can get, if you go down to PB Tech, for example, you can get RS232 to USB connector for $20. You can actually use it as a full documenting calibrator. So you could actually, like you're both ProLEC people?
No, we're both Graham's done that.
Oh yeah, oh, okay. If you were contracting to someone, you could make a job of being a calibration tech and producing certs, because effectively this will produce a cert.
Alright.
Save as found. Any questions about that?
No. You do the same thing for thermocouples.
Yeah. Everything we've talked about. There's a couple of buttons that don't do anything. On this model there is no heart. On this model there is no pressure. If it's a pressure model, there'll be a pressure port there. So that button will just beep annoyingly at you, as will that one. But any of these other functions, yes, just it will just source measure. You know, if you go to ohms, you might have some old-fashioned things, the Honeywell pressure troll, remember those? They have a pot that goes from 0 to 400 ohms. A lot of automotive stuff has potentiometers 0 to 400. So again, you can simulate that or measure it.
Okay, cool.
It is a beast. You'll be so delighted you bought that.
Yeah.
Are there any applications that you might have that Greg's not covered?
Can it confirm a flow rate?
Not in an actual flow. It can confirm the pulses.
What if it's 4 to 20 out?
It will tell you the 4 to 20,
Yeah.
but it can't confirm that it's so many litres.
Can I say 4 milliamps equals this?
No.
2.1 milliamps
No.
equals,
No, you can measure the current and you can simulate the current, but you can't convert that to a flow rate.
right.
It should be. It's pretty simple, I guess, once you know what the transmitter is supposed to be doing in terms of, 10 litres is 4 milliamps, 100 litres is 20. It's fairly easy to do that, 16 minus 4 over the total.
Yeah.
Good question. I knew I brought it along. Anything else you want to know?
I'm good.
This isn't a one-time deal. If you have questions, I'm quite happy to take your call.
Is there software that comes with it now for the time?
Yes, it's free. If you go to Additel, I'll send you a link, or you can go to additel.com. Go to, if you search on Additel Land,
Can I send us the link?
I'll send you the link. Have I got your email address?
Just send it.
What's your name again?
Thomas.
Thomas, that's right. Actually, I haven't got it because you put it on the meeting request.
Yeah.
So I'll send it to both of you, just if you want to. And as I said, literally, I can sell you one from Additel, which I know will work every time, but it's $150. You can go down to PB Tech. You may have to mess around with some drivers, but it'll be $20, $30,
Okay.
literally.
Yeah.
But yes, if you think of anything else, let me know. In the back, it's a rechargeable battery, it lasts for ages. So you just charge it by plugging into the power. The built-in PRT sensor if you want to do your own ice point. So in theory, in 12 months' time, you might want to bring it back and we'll send it to America to get calibrated.
Okay.
Most people are not going to. You can do an ice point, take out the PRT, which is on a long lead, put it into an ice slurry, and set your 0 point for the temperature.
Right.
If you want to do your own cal.
The question I did have is that cold junction
Yeah.
combination factor based on the ambient temperature.
Yes, it's based on that
So
PRT.
that PRT, that's the ambient temperature of the room, right? Now if I point a PT100 into it, it should be pretty close to the ambient temperature, isn't it?
Yeah.
Or it's not.
If it's not, so, well, if it's a PT100, it's not using cold temperature junction. It's measuring resistance.
Right, same drill, but a K-type probe. Like K-type probe, we know the ambient temperature.
You're
that
measuring or
K-type-
sourcing? No, you're measuring.
That K-type probe should be pretty close to the ambient temperature of the room.
Right. It won't matter because the cold temperature. In the old days, when they first came up with the idea of thermocouples, and Mr. Seebeck came up with the whole principle of that, you had one junction here, another junction here, and this junction was in an ice bath. The thermocouple as it stands doesn't actually produce any millivolts. When we teach people and we say a thermocouple works by two different dissimilar metals, produces a millivolt signal there.
Yes.
No, it don't. They're lying to you.
Right.
It's simplicity. What in fact happens is instead of a bucket of ice, you have a cold temperature calibration electronically. Don't worry about it. Basically, thermocouples, forget about it. The PRT is, and the cold temp, I actually conflated 2 points. The PRT is more for your calibration. The cold temperature calibration is done electronically inside.
Yes.
You just don't need to worry about it. This is true of every thermocouple multimeter, every thermocouple device you measure.
Now I've got a device that has been sitting in the room, so Paul went over there.
No, the next one next door.
We know the ambient temperature of the room based on that.
In there.
Yes.
You go where? No.
Shouldn't the probe be fairly similar?
No, it doesn't matter.
Okay.
Because you are comparing it to the electronic bucket of ice,
Right.
which is always adjusted. every thermometer you have that measures, that has a thermocouple, has a cold junction temperature electronic sensor in there, which does take the ambient and adjust for that, but it doesn't affect the reading because you're still just generating a millivolt signal.
Yeah.
So don't worry about the ambient. The ambient has no effect.
But that K-type temperature that I'm getting off that probe is 100% accurate based on that visibility.
Yes.
Now, as the ambient temperature of the room rises,
Yes.
what happens to my temperature?
It won't affect it. It will automatically compensate and know that the cold temperature has to be different.
That's what I thought it would be.
Yeah.
So it should, as the temperature fluctuates ambiently, temperature should be stable.
Correct. It should have no effect at all. Because electronically there's some sort of sensor that's going,
Right.
ambient is this, so I'll make the cold temperature junction move by this amount.
Correct.
Alright. But yeah, if you have questions, just by all
But
means.
whenever that punches out, I can rely on that 100%.
Yeah,
That's
you can
the
you
temperature.
can bet the farm
Oh, okay, that's amazing.
on what that does.
If I'm, so the same thing, if I want to go around and test a bunch of probes, I should create a job, a task.
You could
So
do,
I
it
can store
depends.
that data. But if I'm testing something without a task, and I want to save that data, is that an option?
No.
So it doesn't save everything you tested.
No.
Unless you create a task.
Most times you're probably not going to need to. I mean, if you wanted to double check, you can look at millivolt tables. So if you just go to Google and go millivolt temperature tables, it will say a K-type thermocouple will always, no matter whose brand, be so many millivolts at and that's what it will do. And you'll see on here, it will show that. So if we go to thermocouple, we're going to source a K-type thermocouple at 423.8 degrees. That is 16.474 millivolts.
That's right.
Always.
That's what we're putting out, and then whatever we're connected to needs to be compensation for that to get to that.
Yes, and does automatically. You don't need to think about cold temperature. I mentioned it just from a purely nerdy perspective.
Oh, well, we're having problems in the field. That's unrelated, but
Right.
sort of.
Yeah. All right. So yeah, if you think of anything else, yell out.
Cool.
But you're going to love it. These two you're going to love. These are great, especially if you're nerdy at home. All the screwdriver bits are in the base. Big computers, glasses and things. I use mine all the time.
Oh, thank you.
Very well.